Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 12. So, in which we will continue with our previous lectures article on steady flow through wells. So, in lecture number 11 we discussed the steady flow through a confined into a well through a confined aquifer. So, in which the confined aquifer thickness was B and the well was fully penetrating the entire thickness of the confined aquifer, and the water table was horizontal before the pumping began, which resulted in a steady flow into the aquifer, into the well, and which also resulted in a steady discharge of Q from the well. And we got the expression for the discharge, which is popularly known as the this is the expression, and the original expression in terms of the hydraulic conductivity is Q is equal to 2 pi K into B H2 minus H1 divided by natural log of R2 by R1. So, this is popularly known as the Thames equation, and this, when we simplify, and assume applying the boundary conditions at the extreme points, that is the extreme point wherein there is no drawdown and the radius is equal to the radius of influence R, capital R, and H, the head, is equal to the total head or the piezometric head, and at so this is the upstream most extreme, and the downstream most extreme is a cylindrical wall where this S, the drawdown is equal to the drawdown in the well equal to SW, R1 is equal to the radius of the well, that is RW, and H1, the head, is equal to the depth of the water in the well in the confined aquifer. So, we get this expression, and these expressions can be used in case of pumping test to determine the hydraulic the aquifer parameters such as the hydraulic conductivity and transmissivity. So, therefore, so these expressions can be used in steady flow pumping tests for fully penetrating wells in confined aquifer for determining the hydraulic conductivity K and the transmissibility or transmissibility T of the aquifer. So, here we get an expression for the hydraulic conductivity K for the steady pumping test through the confined aquifer having a fully penetrating well as Q divided by 2 pi b into H2 minus H1 into natural log of R2 by R1. The same thing can also be written as Q divided by 2 pi b, and in this case that is SW and natural log of R divided by RW. So, here this is the expression for K in a steady flow pumping test through a fully penetrating well in a confined aquifer. Similarly, the same expression using these equations, we can write down the expression for T as Q divided by 2 pi to H2 minus H1 into natural log of R2 by R1 this can also be written as Q divided by 2 pi into SW into natural log of R, the radius of influence, divided by RW, the well radius. So, this is the expression for K comma T. So, this is the expression for K and this is the expression for T. So, in a steady flow pumping test through a fully penetrating well in a confined aquifer. So, we need to know to determine this hydraulic conductivity K and transmissivity T, we need to know the steady flow rate from this fully penetrating well in a confined aquifer. We need to know the thickness of the confined aquifer. We need to know either the depths between the observation wells, the depths of water in 2 observation wells, that is H1 and H2, and their radii with respect to their radial distance with respect to the well axis, the vertical well axis R1 and R2, and either we need to know these H1, H2, R1, R2, or we need to know the well radius RW, the drawdown in the well SW, and the radius of influence, that is capital R. And so, in this case, so we can easily estimate the value of the 2 of the 3 aquifer parameters formation constants, that is the hydraulic conductivity K and transmissivity or transmissibility T. Now, let us go to the case of steady flow through a fully penetrating well in an unconfined aquifer. So far we have seen the steady flow through a fully penetrating well in a confined aquifer, and now let us go to this steady flow through a fully penetrating well in an unconfined aquifer. So, for this the diagram would be there is a well which is fully penetrating through an unconfined aquifer, and in this case this is the water surface, that is the water table before the pumping started. And after the pumping started, so this water table will show a steady drawdown so this is the well axis and this is the steady discharge from this well in the unconfined aquifer, and this is the lower impervious strata for the unconfined aquifer. And this is the radius of the well is R w and the diameter is 2 R w, and this is the radius of the influence or radius of influence, radius of the circle of influence is R, and the head there measured above the bottom impervious layer as capital H, and at any 2 points, and here what happens is, so this is the we need to apply the Dupit's assumptions, and so this is the water table by Dupit's assumptions, and this is the true water table. And here this is H 1 and the drawdown there is S1, and similarly for the second observation well, the head is H2 and the drawdown there is S2. And obviously, here the Dupit's assumptions, which we discussed in the previous lecture, are considered, that is applied. So, the Dupit's assumptions accordingly, that is say for small inclinations of free surface, the streamlines can be approximated as or assumed as horizontal. And second assumption is the hydraulic gradient is equal to slope of free surface and is independent of depth. So, is independent, let me write here, independent of depth. So, here the first assumption, that is the streamlines are assumed to be horizontal. So, this is more or less true except close to the well, where the streamlines are significantly deviating from this one, but still with these assumptions the that means the error in estimating the discharge is quite less. So, therefore, because if we consider the inclination of the streamlines near to the well, so then we have to modify our expression and for the discharge, and it will make it more complicated. It will make the expression more complicated. So, therefore, we are making the two Dupit's assumptions, and so here the this one. So, let me show you the flow that is radially into the well, and here this is HW and this is SW, okay, and at any general point this is H at a distance of R from the well axis, the drawdown is S. Okay. So, now we will derive the expression for this steady flow. So, we know that the radially inward velocity Vr is given by k into dH by dr. This is by Darcy's law, and so this is by Darcy's law. So, therefore, the steady flow rate through the well is given by this Vr into the area which contributes, and that area which is contributing in this case will be equal to 2 pi r, which is the circumference of the circle at that radial distance r, multiplied by h, which is the depth of water at measured with respect to the horizontal impervious floor, multiplied by, this is the area, multiplied by the velocity, that is V r, and this is equal to 2 pi r h into k into d h by d r. So, therefore, we can write this as q divided by 2 pi into k into dr by r. This is equal to h d h. Okay. So, this expression needs to be integrated, that is between the limits r 1, the lower limit r 1 and the upper limit r 2, and for the h, the lower limit is h 1, the upper limit is h 2. So, therefore, we get q is equal to pi k h 2 square minus h 1 square divided by natural log of r 2 by r 1, and in this case, so this is the expression for the flow rate. So, at the extreme points, so here this case, that is h 2 is equal to h, r 2 is equal to r, and h 1 is equal to h w, r 1 is equal to r w. So, therefore, this expression can be rewritten as q is equal to pi into k into h square minus h w square divided by natural log of r divided by r w. So, these are the expressions for the steady flow rate in terms of the hydraulic conductivity K, H, which is the depth of water above the impervious layer, in the unconfined aquifer, H w is the depth of water in the well, and r is the radius of influence, r w is the well radius. And of course, if you express the same thing for two observation wells, in that case, so this is the expression, two observation wells at a distance of r 1 and r 2, at a radial distance of r 1 and r 2, where the depth of water is h 1 and h 2. So, these are this is the expression. So, now let us So, in this case it should be noted that the time required for achieving a steady state is longer for unconfined aquifer. And so, these two expressions, let us write down the approximate forms. Approximate forms of equations for the steady flow rate Q. So, when SW, that is the drawdown in the well, is very small, so in that case, that is SW is equal to H minus HW is small relative to H. Therefore, H square minus HW square, we can write this as H plus HW into H minus HW. So, this H plus HW is approximately equal to 2H and H minus HW is approximately equal to SW. So, therefore, the approximate expression for the steady flow rate is equal to two pi, or that is pi into k into 2H SW divided by natural log of R divided by RW, and this can be written as 2 pi into T into SW divided by natural log of R divided by RW. So, these are the this is one approximate expression for Q when this SW is very small. Similarly, this we can also write this Q is approximately equal to 2 pi into T into S1 minus S2 divided by natural log of R2 by R1. So, in this case, that is so here that is H2 square minus H1 square. So, here that is assuming H2 square minus H1 square is equal to H2 plus H1 into H2 minus H1, and this H2 plus H1 we can take this to be approximately equal to, that is 2 T 2, that is H into, and this S2. So, this is S2 H2 minus H1 is equal to S2 minus S1. So, therefore, we get this expression, that is so, these two expressions will give the approximate expressions for the steady flow rate through this fully penetrating well in an unconfined aquifer, and obviously they are almost the same as the expressions for steady flow through a fully penetrating well in a confined aquifer. So, now we have discussed the steady flow through a fully penetrating well in an unconfined aquifer, as well as a fully penetrating well in a confined aquifer. And now, in this case, so here we can also write down. So, therefore, this T is approximated as K into H1 plus H2 by 2. So, therefore, this K into H1 plus H2 is equal to 2T. So, this is with this assumption. So, we get this approximate expression for this Q. Now, let us consider the unconfined aquifer it is unconfined aquifer with uniform recharge. So, in these previous two cases, we did not consider any recharge into the well. So, now let us consider the unconfined aquifer with uniform recharge. So, in this case, that is this is the ground level, and this is the well in the unconfined aquifer, and this is the water table, and of course, so here we are getting the uniform recharge. And let us take this as W, recharge rate W, and this is the steady flow through this well is QW, and here so this is the lower impermeable strata, and let us consider a strip wherein the inflow is Q and outflow is Q plus dq. So, this dq is the one which gets contribution from this recharge, the constant recharge, and in this case let us consider the water table. and let us consider the steady height as say h0 and the radius of influence as r0. And here, so this radius is r, and then for this elemental strip of radial distance dr. Okay. So, now we can write down for this case we can write down the expression for the discharge dq is given by the area, that is minus 2 pi r into dr into the uniform rate of recharge. So, if we integrate this one, we get, that is q is equal to minus pi into r square into w plus the constant of integration, and the boundary conditions are at the well r tends to 0 and q tends to qw. Therefore, qw is equal to c. Therefore, we can write down this q is equal to minus pi r square into w plus qw. Okay. And if we substitute the expression for q, which is minus 2 pi r k into h dh by dr. So, here this k into dh by dr is the velocity as per Darcy's law, and 2 pi r into h is the area which contributes flow. So, this is equal to minus pi r square into w plus qw. So, if you integrate this expression, integrating applying the boundary condition, it is h is equal to h0, the upstreammost boundary condition, and at r is equal to r0. So, therefore, we can write down after integration, we will get an expression for the drawdown curve h0 square minus h square will be equal to, this is w divided by 2k into r square minus r0 square plus qw divided by pi k into natural log of r0 by r. So, this is the expression for this drawdown curve. In an unconfined aquifer with uniform recharge. Okay. So, if we know the value of the depth of water above the lower impervious layer, the uniform rate of recharge, hydraulic conductivity, and the radius of influence R0, QW, which is the steady flow through this well fully penetrating the unconfined aquifer. So, in that case, so this will be the expression for the drawdown, and we know that when R is equal to R0, Q is equal to 0. That means, beyond this the cone of influence, there is no flow contribution. So, therefore, substituting these values, we get QW is equal to pi into R0 square into W. In this case, so that is so when R is equal to R0, in that case, so this Q is equal to 0. So, therefore, if you apply this expression, so in that case this QW is equal to pi into R0 square into W. So, therefore, so this is the expression for the steady flow through this well in an unconfined aquifer having a uniform recharge, and this is the expression for steady flow through a fully penetrating well in a confined aquifer, in an unconfined aquifer, with uniform recharge. So, it is fairly simple. So, simply the area of the circle of influence multiplied by the uniform rate of recharge. So, that will be given by, that will give the expression for the steady flow through the well. And now, let us consider a well in a uniform flow. Uniform flow through an unconfined aquifer. So, again this is a a fully penetrating well in a uniform flow through. So far we have considered the water table to be horizontal, so that only after the pumping starts the well starts getting contribution from the aquifer. Now, instead of that, suppose we consider a well which is drilled through an unconfined aquifer having a sloping water table below the sloping ground. In this case, let us consider, so this is the sloping water table, so with slope of I, okay, and let me denote the well axis here, and the uniform discharge through this well. And here what happens is, after the pumping starts, then the water table will show a drawdown curve like this. So, this is the drawdown curve. And in this case, obviously here so up to this point only there will be contribution to the well, and obviously on this the right side it is fully flowing, this one. And if you draw the, so in this case let us I am sorry, so this is let us say this is a confined aquifer, and here this is the top confining layer, and the confined aquifer thickness is B, and now in let me, so this represents the stagnation this vertical line represents stagnation, and let us also draw the top view for this if this is the, let me draw the top view. In this case, this is the well, and let me So, here this represents the stagnation surface, and within this so these are the streamlines. And so here at any let us consider this as plus YL, and let us consider this as no, I am sorry. So, this plus YL goes all the way up to here. This is minus YL, and this is this distance is say minus XL, and obviously, so this is the x and y coordinate, and beyond this the flow lines will be like this. Okay. So, now for this case, so there is a stagnation surface because of the original slope, that is the original hydraulic gradient due to an inclined water table. So, in this case we can write down the expression for the hydraulic conductivity as 2q, k is equal to 2q divided by pi into r into hu plus hd into iu plus id, and where here this hu is the upstream saturated thickness, HD is the downstream saturated thickness, and this IU is the upstream water table slope, and ID, this is the downstream water table slope. So, by superimposing radial flow and 1D flow, we can write down the expression for this the stagnation surface, that is y by minus y by x is equal to tan of 2 pi k bi divided by q into y. So, this is the expression. So, this B is the saturated that is the aquifer thickness, and Q is a steady discharge, and of course, I am not going into the derivation of this. So, therefore, and this YL is given by plus or minus Q divided by 2K BI. So, this is the distance of the stagnation surface at a distance and okay, and XL is given by minus Q divided by 2 pi K BI. So, we will stop here and we will continue in the next lecture. Thank you. Bye.